So I'm Josh. I will be talking about how we want to use a writing to learn assignment to identify misconceptions in acid-base chemistry in an introductory organic chemistry course. This was under the guidance of Stephanie Nez, who's here. So acid-base chemistry, for those that haven't taken organic chemistry in a while, is really important. The American Chemical Society puts it up in one of the top 10 major topics to be studied in introductory sequences. A recent analysis over the top organic and biochemical reactions taught throughout college shows that 86% of them require a really good understanding of acid-base chemistry. And through these analyses, there's been several intended learning outcomes that have been identified to be important, and of them include comparing two acids, determine which one is relatively more or less acidic, apply certain factors, basically be able to look at the structure of the molecule and understand how certain features impact acidity, and then using pKa, which we'll go over in a second, determine the relative acidity of a series of molecules, and where pKa is just a quantitative metric. The lower the number, the more acidic. The higher the number, the less acidic. And this is based on different functionalities, different orientations of atoms and bonds within the molecule. And we teach students in these introductory series certain structural features that are important to determine relative acidity. But the problem is that students are very good at coming up with little tricks and ways to get around multiple choice questions when they don't really have a fundamental understanding of this material. So it's been decided by several educational scholars to start having them write more because it's really hard to hide behind 500, 700 words of text if you have misconceptions in something. So this has been recently utilized for several different chemical features and ideas, but hasn't really been implemented as much in acid-base chemistry. So I thought, well, maybe we could have the students develop a question, which we'll go over in a second, using a writing to learn assignment. And that could be used to identify some misconceptions that they might have in acid-base chemistry. Maybe this could be a tool we use to identify misconceptions. So that was the research question. Can a writing to learn assignment help identify student misconceptions in acid-base chemistry within a 10-week introductory organic chemistry course? And this was in Dr. Nez's course. It was a 10-week course. It's the first of 3 quarters of an organic chemistry series, and the students were majors and non-majors, and there was 85 of them. So the topic, again, was ranking relative acid strengths, and this was selected based on the literature, common things that students have trouble with in organic chemistry, and also by Dr. Nez, who has seen that her students have struggled with this in her classroom. So the writing to learn assignment that I developed was an optional bonus assignment that went towards their concept check grade. So it could be bonus points that could have helped their grade a little bit as some motivation. And of the 85 students, 45 submitted them. And this was performed pretty early on in the course. So it started at the end of March, and it was only a couple weeks later after they'd learned everything about acid-base chemistry. So they'd done all their lectures for acid-base chemistry, and then we did this writing to learn assignment. So this was what the writing to learn assignment looked like, and this is the design of this is based off the literature, where there's usually some authentic rhetorical context as motivation. In this case, I tell them that they're going to be professors and they're trying to work with a colleague to develop a question to trick their students, and they're going to try to figure out what they know and don't know. I have a series of molecules and I tell them to rank their acidity. I do not give them pKa. I don't give them a numerical value. They have to do it based on structural features or orientations of the atoms. And then there's specific instructions. This is so that all the answers are similar to one another, that the responses are long enough that I could draw out misconceptions if they have them. And in these instructions, there's 1 correct answer and 3 incorrect answers, which will be shown in a second. And then there'll also be motivation. So this is the points that I try to use to motivate them to do this. But yeah, so here we have the list of molecules, and in all of their responses, they had 1 identified correct answer. So where the ordering they thought was correctly ordered, and then 3 where they felt they were incorrectly ordered, and they incorrectly ordered them in a way to try to draw misconceptions out of the students. And then there is this long justification where they go through each of one of these responses and explain why they designed them the way they did. And these were designed in a way to help them do that. So there's these clusters, and we don't need to go into the details of the chemistry, but basically between this molecule and this molecule, if they flip them in their correct answer, I know that they have some issue with resonance. And if they flip these two, I know they have an issue with induction. So I designed the question in a way where I could use this cluster analysis to be able to really quickly see what students might have issues with based on their answers. And this also speeds up analysis. Writing to learn responses are challenging in the literature because it takes so long to read through all the students' responses. So I thought this might be a tool to actually quicken them up and actually be able to get more information out of them. But again, this isn't enough. You need to read the justifications. So I came up with a rubric where I not only analyzed their correct answer in the clusters in their correct answer, but then I went through their justifications and I scored them from 1 to 3 for each of these different structural effects, where 3 is consistently accurate explanations of the concept throughout their written response, 2 is inconsistently accurate explanations, and 1 is an inaccurate explanation of the concept. So then I did this for all the students' responses, and I was able to tabulate them to get some information. So if we look at all the responses and the analysis of them, of the correct answers that students identified as correct answers, 58% of them were properly ordered. I thought this was really great because that meant that the question was sufficiently difficult enough to draw information about the students' misconceptions, and therefore a little bit less than half of these correct answers were improperly ordered. So if we go through the improperly ordered responses, we could get an understanding through this cluster analysis what might be the cause of their improperly ordered correct answer. And we see it's a mixture of several different structural effects that they were taught in the class. But again, justification needs to be analyzed because this isn't enough to know exactly why. What is the misconception that these students have? So when we go through the justification analysis, I could separate it, their scores based on those that properly ordered their correct answer and those who improperly ordered their correct answer. What we see is that the students are really good at understanding the relationship between pKa and acidity. So if I was to give them numbers, for example, of the pKa's of each of these molecules, they'd be great at understanding how to order them. But there is a significant difference between their accuracy and their understanding of resonance and induction, these two different structural effects that I was testing them on. The students that had the properly ordered correct answer, even they didn't have a perfect understanding of these two responses, suggesting that if this was given as a multiple choice question, a lot of students would have been able to get the correct answer, but still not have a really accurate understanding of this material. And those that had improperly ordered correct answers had really inaccurate understandings of both resonance and induction. And while these numbers are great, I still don't necessarily understand what the misconception is. So using this, I was able to pinpoint, I went through their justifications and I looked for commonalities. And we don't need to go through the specifics of this, but there was something, an error, that I was able to identify through the relative orderings of these 3 molecules, where they would have this error in what was called an oxoacid rule error. They misunderstood the relationship between the number of oxygens in the molecule and acidity, and they had this misconception that resonance was really, really powerful compared to everything else we taught, and this was seen throughout a lot of the responses. And I had no idea that they'd have these issues, but the students did, which I thought was really interesting. We talk about this all the time, how we're a little bit disconnected from the students because it's so long ago since we learned this material that it's maybe a little bit harder for us to understand the issues that students have with the material. But the students, in their responses, their incorrect responses, designed them because they knew that their colleagues would have issues with these 2 problems, which I thought was great. And this was seen multiple times. But in conclusion, the Writing to Learn assignment was a very effective, non-invasive tool to pinpoint student misconceptions in acid-base chemistry. I was able to determine exactly what misconceptions they had on this topic, and I just had to have them write an assignment, and using the cluster analysis to help me pinpoint where to look, it only really took 3-4 minutes an analysis for each student's response. The students were able to answer multiple choice answers correctly, would have been able to answer multiple choice answers correctly with inaccurate understandings of the material. The students have a very good understanding of pKa, but have inaccurate understandings of these 2 different rules that we taught them in the classroom. And then another important point, students should be taught how to use resources more effectively. I showed that both groups of students were able to understand PKA really well. So if I was to give them the PKAs, then they should have been able to orient them perfectly. We gave them a PKA table in the assignments, but all these molecules are also online. There's a Wikipedia page for each one of these with identified PKAs. So if they just Googled it for 5 seconds, they should have all had the proper alignment, orientation of these molecules. And it's been shown in the literature that students are not really taught in an undergraduate setting how to use these resources effectively. So this is something that stood out to me, that we should look at in the future as well. But overall, I think this is a powerful tool to gauge student understanding within a class in real time, and that in the future we could use this to improve learning outcomes. We could inform future lectures to target identified misconceptions. We could better design our homework questions, our quiz questions, our exam questions, and then we could study if this tool is effective to enhance student learning outcomes. And we could cycle topics. You know, one quarter of semester we do this on acid base. The next one we do it on something else. But yeah, that's what I have. If anyone has any questions, I'd love to answer.